Hi, this is Professor Fernandez working on Class Notes B in Lesson 17. In this example, I want to tie together the notions of an equilibrium solution, which we've defined in this lesson, with our physical intuition about what the equilibrium of a system is, the equilibrium states of the system. So I say that in lesson 4, we developed a model for the vertical displacement of a mass from its equilibrium position in the free vibrations case. So I'm referring here to this little picture to remind you. We had put this mass on a spring, and then the idea was we were going to let it go as we pulled the mass down, and it was going to oscillate up and down. And in lesson 4, we had developed this nice model for the vertical displacement of the mass, and that was this second order ODE. So what I'm going to do here is, first of all, convert this to a system of two first order ODEs using the substitution that we first talked about in lesson 14. If you remember, that substitution was x1 equals y, x2 equals y prime. But in this lesson, I've been using x and y for the independent, for the dependent variables, not x1 and x2. But you can see things will get a little confusing if I use y and it's equal to y prime here, right? So I'm going to, instead of using y on the left-hand side, I've decided to use the letter z. So that explains why I'm using this substitution here. But it's the same structure of the substitution as what we did in lesson 14. Okay, so we're going to use that substitution and convert this second order ODE into a system of first order ODEs. Let's see how that goes. So we have x equals z, and then z equals y prime. So the first thing I do is I take x and I differentiate it, and I get z prime. Remember, dots and primes are the same for our course. And then I use the fact that, x equals y. I wrote down the substitution incorrectly, so x equals y, so x dot is y prime. And then I go over here and I use the fact that y prime is z. So I'm going to put equals z over here. So that's my first equation in the system. I'm going to write the system down here. X dot equals z. And now I go back and do the same thing, but starting with the z equation. So z dot is the second derivative of y. And now I'm going to go back to the system, and I am going to solve here for y double prime. So what do I get? I get y double prime equals minus ky over m. All right, so I'm going to put that in here, equals minus k over my. And y is what I had called x, so I'm going to substitute that in here, minus k over mx. And that is my second equation in the system. Z dot equals minus k over mx. All right, so these are my two equations that are equivalent to this one second order ODE system. So that's part A. Now let's talk about part B. So in part B, what are we doing? We are going to calculate the equilibrium solutions of the system in part A, and then we're going to interpret them. So this is when we're going to tie in the math and the real world's intuition behind equilibrium. Okay, so calculate the equilibrium solutions. First of all, let me just notice that we know this is another way notation to write this, which is more along the lines of the way that we wrote the system in the previous video, the way that it was presented. But anyway, same same notion applies. If you want to find the equilibrium solutions to these type of systems, you want the right-hand sides to be zero simultaneously. So as we did in the previous video, I suggested set the first right-hand side equal to 0, set the second right-hand side equal to 0, and then solve. This happens to be a simpler system, so we don't have to solve for anything there. And for here, we can just multiply by m divided by k and divide by minus 1 and get x equals 0. So the only equilibrium solution is x equals 0, z equals 0. All right, written in vector form, that is the vector where we're thinking of our vectors here as having components x of t and z of t, which again, based on our substitution, is y of t, y prime of t. Okay, so writing this in the vector form, well, we just have a component here that's 0 and another one here that's 0. So our equilibrium solution in vector form is 0, 0. Okay, so we found mathematically the only equilibrium solution, 0, 0. Now let's go back and interpret this physically. So to do that, I'm going to go back to what x and z mean in the context of this problem. So first, let me remove some of the clutter, and then we'll talk about where we can go to see what x and y mean. So I'm going to go first to the definition where we first used them. So x and z are up here. So x equals 0 implies that y equals 0. So that's from here. And z equals 0 implies that y prime equals 0. That's from there. So now I'm going to interpret this information, and particularly this information, in the context of our diagram. And remember, we had defined our coordinate system to be positive downward, and we had defined the displacement of the mass to be y of t. So this condition tells me that the mass is not displaced from its physical equilibrium position, which is when it's just kind of like hanging out there. You first put it on the spring, don't do anything to it, let it kind of settle down and wait for a little while. Come back, and that's y equals 0. This condition is the derivative of y. So y is a displacement, so it's a position function, and take its derivative gives you the velocity. So this condition tells me that the mass is not moving. All right. So this is kind of something that we expected, that the equilibrium position for this system would be literally just the mass hanging on the spring and not moving anywhere. But again, it's really nice that given the mathematical model that we developed for this system, we have now proven mathematically that these are the only equilibrium solutions. And that's a much stronger statement. Certainly if you walked into a lab and you saw a mass hanging on a spring, and your instructor said, how would you describe the physical state of that system? You would say, oh, it's in equilibrium. If your instructor then said, is that the only such equilibrium state that's possible for this system? That's a slightly more challenging question. Mathematically, now that we have this model, at least within the parameters of the assumptions of the model, we have just shown that in fact this is the only equilibrium state of the system. So that's it for this video. In the next one, we will analyze a different system, the pendulum, which has more than one equilibrium state.